Okay, thought I'd start with a photo of my daughter just at the exact moment of a phase transition. And so what shall we do? Okay, so I'm going to talk about some, whoops. I'm talking about Matroids with 9 elements, which is a sort of a story that I'm going to tell about the use of computer catalogs in Matroid theory. So it should be nice and relaxing. There's not too much in the way of proofs or anything like that. Suitable for a relaxed afternoon pre-soccer. It was done, this is work that I did with Dylan Mayhew, who's currently a postdoc in Wellington at Victoria University, working with Jeff Whittle. So 3 parts to the talk. I'm going to start with definitions for those people who are not completely familiar with Matroids, just to make sure that everyone's on the same page. If you are familiar, then you can just pick holes in what I say. Then talk about the computation, and then I'm going to talk about how the resulting database of actual Matroids can be used. I'll give some examples of that. Okay, so let's start off with some definitions. So, what is a matroid? Well, a matroid is a combinatorial generalization of a vector space, basically. It arises naturally when you attempt to axiomatize the properties that are enjoyed by, or possibly endured by, vector spaces. In principle, it provides a unified approach to problems in lots of diverse areas, because once you've axiomatized a matroid, then any of the models of those axioms, which include vector spaces, graphs, transversals, and so on, you should be able to tackle some problems in those areas in the unified framework of matroids in general. Okay, so what's the actual definition and how did it arise? It arose from a definition by Hassler-Whitney, and he was looking at matrices and thought of the word matroid as a sort of extension or generalization of that word. And he was considering the columns of a matrix as vectors over a field, elements of a vector space, if you like. And he was trying to think, what are the axioms for being, for a set of columns to be independent? So you want to come up with some axioms that captures independence without using the field and the actual, linear combination, something to 0 type of thing. And he sort of worked away and came up with the following 2 axioms. If you've got an independent set of columns, then any subset of that set of columns is also independent. So that's the standard hereditary property of independent sets. And then the exchange property, which says that if you've got a set of p columns that's independent, and you've got a bigger set of size p plus 1 that's independent, well, then you can flip one of the columns from the bigger set to the smaller set and remain independent. Okay, why did he think of columns of a matrix instead of just vectors in a vector space? I think really just to make it easier to think about the situation when 2 columns are the same, or a column is 0, or something like that, just so that you don't sort of have to phrase everything in terms of multi-sets and so on. Okay, so a matroid then is just any set together with a collection of subsets of that set that satisfy the 2 conditions.
Plus the trivial condition that the empty set.
Oh yes, the empty set's independent. Sorry. Okay, so here's an example, and seeing we're axiomatizing columns of matrices over, columns of matrices over a field, then if you actually take a column of matrices, columns of a matrix over a field, then you're going to get a matroid. So 1, 2, 3. Well, there's 3 columns, they're an independent set, so that's independent, and so all of the subsets are. 7 is dependent, because it's just the 0 vector. 5 and 6 are dependent, because they're both the same vector, and so on. So, when you axiomatize something, you hope that you capture your original, the nice properties of the thing you were trying to axiomatize, so that you can then get something that contains the nice things you were trying to axiomatize, but not too much else, or you don't lose too many of the properties. Well, a nice property of vector space is that all the bases have the same size. That's sort of a fundamental property of a vector space, and it's true for a matroid as well, where we just define a base of a matroid or a basis of a matroid to be any set that is independent and maximal with that property. Graphs give you matroids in a number of different ways. This is the way that's sometimes called the cycle matroid. Just take any graph, can be a multigraph, loops as well if you wish, and define the independent sets to be any subsets of the edges that induce a forest or a tree, a graph with no cycles. It's clear that if you have something with no cycles and you take a subset, then you also have something with no cycles. It's clear that the empty set induces no cycles, and you've just got to check the exchange axiom, which is sort of easy to do, but I'm not going to do it right now. The bases are the spanning trees of the graph. So the bases of the matroid are the biggest things that are independent, to have no cycles. If you add any edge to a spanning tree, you'll create a cycle. If you hear a word in a matroid talk that you don't understand, basically there's a good chance that it arises from graph theory or from linear algebra, and if you sort of make a guess of what that means in that context, then it will generalize to matroids. So any set that is dependent is just anything that's not independent. A circuit is a minimal dependent set, so a circuit is a cycle, essentially. The rank of a subset, the rank of a set, a subset of your element set, is just the size of the largest independent set contained in it, just as in linear algebra. A flat is the analog of a subspace, a set of points such that when you add anything else, you increase the rank. And hyperplanes are special flats, which are the flats of the biggest dimension they can be, -1. So all that terminology is either from graphs or from linear algebra. Now, the trouble is there are lots of other things you get when you're doing this definition. This axiomatization captures graphs and vector spaces, but it also captures a whole lot of other things which you may not think of as very interesting, like the uniform matroid, URN. It's got every set of size less than or equal to R is independent, and then every set of size R or above has rank R. So you have a very flat sort of structure.
But this is geometrically kind of interesting. This is endpoints in general position in R space.
That's right. That's true. Yep. Yep. So take endpoints in general position in R space, take any subset of fewer than R of them, and you get an independent set. But as soon as you have got R of them, then you span everything, and you can't go any further. So I guess it is a natural linear algebra concept.
That also means that a uniform matroid can be embedded in any sufficiently large field. All right? I mean, it's a vector matroid over any sufficiently large field, so that you can handle a general position.
Can you do that with a graph also, or with a graph itself?
A graph you can't do. What can you do? What's the question?
URN for arbitrary R and
No.
No.
Oh, is URN graphic?
No.
U24.
Even as soon as you get to U24, it's no longer isomorphic to a matroid obtained from a graph. So as soon as these are called lines sometimes, the U2 something, and that immediately stops you from being graphic, and you launch into geometric structures then.
Basically, the only graphic ones are R equals 0, 1, n minus 1, or n.
Yeah, that's right. Okay, now the thing about matroids is, well, Okay, so what we've got, we're trying to do sort of graph theory, or maybe we're trying to do a linear algebra, but we've thrown away a lot of stuff. Alan's fond of saying that he now works on graph theory without vertices. He could also say he's doing linear algebra without fields, or something like that.
Geometry without numbers.
Yeah, that's right. There are some operations on matroids which can be easily defined and which generalize natural operations on graphs and vector spaces. Duality is probably one of the fundamental ones. Take your set of bases of a matroid and then individually complement each one. Take the complement of each of those and just look at that set of subsets. Well, that turns out to be also the set of bases of a matroid. You then have to check that the exchange axiom works and things like that, but it does work. So for any matroid, there's a dual matroid. If the matroid's got rank R and you've got an n element set, then the dual matroid has rank n minus R. So matroids come in dual pairs. For graphs, what does it correspond to? Well, in general, nothing, but for planar graphs, we actually know that the dual matroid of a planar graph is itself another graphic matroid. So if you start with a planar graph and you form its dual by putting a vertex in each face of your planar graph and putting a dual edge, a blue edge, across, connecting any two faces that were previously separated by one of your original edges. So the blue graph is the dual, the geometric dual, planar dual. Now, it's sort of fun to do. If you take a spanning tree in your original graph, that's these red edges here, then the complement, which is the dotted red edges, which are now blue in the solid blue in the blue graph, is a spanning tree in the blue graph. So the complement of a spanning tree in a planar graph is a spanning tree in the dual. And so this general operation of matroid duality, has a nice interpretation when you stick to planar graphs.
There is any good reason why the numbers are not consecutive?
That's a very good question. I've got no idea what my brain was doing when I called that 7130.
Maybe any type of graph.
1, 2, 3, 4, 5.
A single type of
No idea.
is okay, maybe.
I think that must be a 2, yeah.
Okay.
They're irrelevant anyway.
I was expecting some trick with that.
Yeah, no. Vertices are irrelevant anyway, so we can call them what we want. Okay, so anyway, the key point is that if you take a graph, take its matroid and dualize, if you take a planar graph, then you get the same thing as if you had dualized the graph and then taken the matroid. So it's a good operation. Now, if G is not planar, then the dual of the Seipel matroid is not a graphic matroid, but it is a matroid. And so you can work with it in the general sense. And so maybe you might think this is good, because now we've got an extended concept of duality that applies to all graphs, as long as you're willing for your universe to expand to matroids, or at least graphic and co-graphic matroids. So, and then this is a useful tool. I've sort of done a lot of graphs. Now we'll go to vector spaces. What does the matroid duality correspond to in a vector space? Well, it corresponds exactly to orthogonal dual in the normal sense. So you can always do row operations on your matrix, and you'll get the same matroid. It doesn't alter which sets of columns are dependent or independent. So you can always put your matrix into this form. You might have to do some column shifts. And the dual is just this matrix, and that's very familiar. If this is a generator matrix of a code, then this is the parity check matrix of the same code. And so the row space of this matrix is just the orthogonal dual of the row space of this matrix. And we're all happy. So duality in representable matroids, the ones that do come from matrices, is just what you want it to be. Okay. almost at the end of the definitions. So deletion of an element is just, you just throw it away, and any independent set that contained it, you just remove it. Or you just throw away that independent set. It's the same thing. For graphic matroids, it corresponds to deleting an edge of your graph, so it's natural. For representable matroids, it corresponds to deleting a column, and so it's natural too. So if you keep doing this, you start with a matroid and you keep throwing away elements many times, and you get something that's called a restriction of your original matroid. Now here's a nice little question that someone would like to know the answer to. Take any rank 3 matroid. So all it's got is points, or elements, which are called points, lines, which are flats of rank 2, and the whole thing is rank 3, so it's the plane. So there's a rank 3 matroid. This is not a projective plane because, so 2, 3, 4 is a line in this matroid, which means it's got rank 2. Here's a line, 2, 3, 4, here's another line, 5, 6, 7. They don't meet, so it's not a projective plane. But maybe you could add another point and extend that line, and then you'd...
Gordon, is that really an open question? Can't you take the Fano plane and the non-Fano matroid and glue them on a line in the same plane to get a non-representable rank 3 matroid?
Well, I'm not saying a finite projective plane, I'm not saying a finite Dizanzian projective plane.
I take it back.
I'm just
What
saying...
does that mean? I don't know any projective geometry.
Dave's question was, if you could do this and you've got a Dizanzian plane, then that would show that any rank 3 matroid is representable.
Projective plane just means you take some field.
No.
No, that's the
Combinatorial.
combinatorial. You just take a set of...
It's not even division ring. It's something
No.
more general.
That's
Yes.
right.
That's what I was missing.
That's right.
I was letting the numbers creep in there, but no.
That's right.
No numbers.
Yeah, so it's a some projective plane, not Dizanzian, that you can
So
complete
there's
that
an
to.
axiomatization of projective geometry, which in dimensions 3 and above gives you ordinary coordinate projective geometry with coordinates. But in dimension 2, there are these exceptional examples that are not coordinatizable.
It's a little bit like matroids. You try to capture linear algebra, and you end up getting matroids that aren't representable over any field at
That's
all.
right. Anyway, it's true if you allow the plane to be infinite. So, okay, the dual operation of deletion is contraction, and I'm cheating by defining it to be the deletion from the dual and then dualizing again, just because the actual definition is a bit fiddly. But for graphic matroids, it just corresponds to contracting an edge in the normal way. For represented matrices, it just corresponds to projection in the ambient vector space onto a hyperplane. If you're a coding theorist, then deletion is shortening and contraction is puncturing a code. So it just follows the natural things. Okay, a minor is something you can get from a matroid by doing any old sequence of deletions and contractions. And much of matroid theory is to do with minor closed families of matroids. So if a matroid is representable over a field, then so are all its minors. And so you might say something like, describe in some other way the matroid is representable over a field, a particular field. And there's lots and lots of work done in minor closed families of matroids. A lot of the work focuses on excluded minors, and that's the minimal things that are not in your family of interest. So you might say, let's take all the matroids that are representable over GF2, binary matroids. What is the smallest matroid that is not representable over GF2, but all of its minors are? And if you can make a finite list of those, then that will characterize binary matroids as, precisely the matroids that do not have this minor or this minor or this minor. And binary matroids were characterized by Tutt in more than 50 years ago as precisely the matroids that do not have U24 as a minor. And a lot of the theory of matroids is, given a closed class find the excluded minors. And then conversely, given some minors that you don't like, can you say anything about the properties of the class you get when you do exclude them?
May I ask, is the theorem that for every class of graphs which are minor closed, the list is always finite, or it is true for Matroids?
It's not true for Matroids.
But
I
true for graphs.
But true for graphs. But it's a very deep theorem for graphs, 25 papers worth of work. It's easily not true for Matroids. It's probably true for Matroids that are representable over a particular finite field, but that's unknown. Okay, so that's the background. So now let me say what we did and why we were looking at computation. Well, computers have been used forever, well, since they were around, in combinatorics to make lists of examples, because people often want to quickly get their hands on some graphs with a certain property in order to, I don't know, compute their flow polynomials or something like that. So there's lots of work that's been done in cataloging graphs, designs, geometries, and so on. You can use them for just count things, or you can look for examples that might have some special properties, or you can try and spot some patterns or whatever. So combinatorics being, because it's discrete and finite, probably has used computers more heavily than most disciplines. Okay, so our starting point was this tech report from University of Waterloo. And in those days, they used to have nice covers on their tech reports.
The same one, or each tech report has
No, this is
an
just
artist made.
this is a once-off.
That's very 60s.
Henry Crapo is a very interesting character. Can you read it?
Yeah,
The Henry Crapo Group presents the incredible catalogue of 8-point geometries. See single element extensions grow before your eyes.
I can't read anything.
Well, here's eyes, E-Y-E-S, and here's the yellow thing is 8. It's all done in sort of psychedelic 60s lettering.
It is really 60s. Yeah.
That's right.
That's awesome.
Yeah, so I met Henry Crapo for the first time in Wellington in December. He's a rather interesting character.
I could have maybe guessed that Craig was his
Has his own personal conference centre in France somewhere. So anyway, so he and his collaborators, Crapo, Blackburn, and Higgs, computed back in 1969 a catalogue of all the 8-element matroids. Okay, so to specify a matroid, you've got your 8 elements, which you might as well call 1 to 8, and then you've got to say, well, what have you got to say? You've got to say what all the independent sets are. So you might have a big list of independent sets. So a matroid doesn't, in general, have a compact representation.
Well, you can skip the ones which are smaller than somebody.
That's right. So you may just choose the bases, and that will give you a list. But you can still have many, many bases, because if you have,
Even in a graph, the number of trees is exponential.
That's right. But in a graph, you wouldn't specify a graph by listing its spanning trees.
Yes, but if it were not a graph.
That's right.
Analogy.
That's exactly. Well, that's a very good analogy. It's like if you were doing graph theory and you had to specify a graph with always by listing its spanning trees, then things would be a lot harder than they are now. So these are the number of
representable, you could give a representation.
If it's representable, you can give a representation. You can just give the set of the columns of a matrix. So there are situations when you can get a compact representation, but those are a minuscule fraction of the total number.
Well, the smallest non-representable matroid has 8 elements, right?
That's right.
But of course, if you wanted to catalog all the other stuff, you'd have to determine for each matroid which field is it representable over.
That's right. And then, yeah.
Furthermore, you will have some isomorphism problems. You don't want to write twice something which is the same up to a change of basis which is arbitrarily big.
That's right. Yeah, exactly. All of these are issues. So anyway, these were the numbers of matroids on 8 elements up to isomorphism. So we've thrown out isomorphic copies. So if you relabel your elements by an element of the symmetric group, then you don't care. So there's 1,700 on 8 elements, so most of them have got rank 4, 940, 8-element rank 4 matroids.
They are monotonically bounded binomials.
Well, you sort of expect it to go up and then down because of just the... So...
Well, symmetry is obvious.
Symmetry is obvious. You have to have symmetry, and so if you've got to have symmetry, then you want the one in the middle to be biggest.
I wanted to say that a huge number of these are just the binomials. You have just a 7 instead of 6,
Oh.
15 instead of 10.
Yeah, it's just chance down at this level. It's just a small number phenomenon.
But in
Yeah.
the middle, it's quite different.
Yeah.
But unimodality, I hadn't thought of that before.
Unknown. Obviously true. Bet you Amy's hand in marriage for it. And
Did she consent?
okay, so well, this catalogue of 8 elements. Now the thing is,
So for rank A, you for 8 elements,
yep,
you need only to look at rank 4.
that's right.
Right.
You can stick to rank 4 because you can just take the duals of all these, and you would get these. Yeah. So you don't have to go all the way.
You have to go up to rank 4.
You have to go up to rank 4.
Can you classify for arbitrary n and that say up to 1 or up to 2?
Well, for rank 1, this sequence is growing in a fairly controllable fashion. So for rank 2, I think we know that too. For rank 3, it explodes. They become...
So this rank 3, which are simple, they have this kind of semi-geometry.
That's right. They're partial linear spaces, so you can represent them geometrically through a picture on
So the game
plane.
is on rank 4.
Well, even rank 3, there's lots of stuff that's not known. So, okay. Did anyone use this catalogue? Well, the trouble is, it was on microfiche, or printed in about a 3-point font, and it was hard to use, right? Because you just have this list of bases or whatever, and how do you use that information? Matroids are hard to work with. My suspicion is that it wasn't used because this theorem was proved in 2000 and won the authors a Fulkerson Prize. They proved that a matroid is representable over GF4 if and only if it doesn't have any of these minors. Now, it doesn't matter what they are, except that they're only on 6, 7, or 8 elements. This matroid came up in their proof, but no one knew of it before as being a candidate for an excluded minor for GF4. But if you'd used that catalogue, you could have found out.
Well, you would have had to use the catalog to
And-
get with some algorithm for testing GF4 representation.
That's right. So GF4 representability, you could easily compute. Yeah, that's right.
But is there any algorithm for given a matroid saying in one go over which finite field
No.
it's representable?
No.
Because in Huxley's book, the answers are usually something having to do with the characteristic of the field and the size of the field.
Yeah,
But it's not even known that it's that simple.
that's right. Yeah. Okay, so in their paper, Blackburn, Crapo, and Higgs said it's unlikely that 9-element geometries will ever, they call them geometries, will either be feasible or desirable. So there'll be many thousands, and they used a sort of a crappy recursion that's known to be much too small and predicted 29,260. Until then I thought, well, okay, I've got 40 years of advances in computers and techniques for combinatorial enumeration. Surely we can do 10 elements. Judging,
You interpolated into their sentence the word ever.
well,
Not in
that's, yes, no, that's true. As you can tell by the title of this talk, we didn't succeed in extending it to 10 elements. One problem is representations. For graphs, life is easy, okay? You use an adjacency matrix if the graph is small. You use adjacency lists if the graph is large but sparse. And if the graph is large and dense, you give up or start doing probabilistic things or something. For a matroid, there's no obvious representation. Ultimately, you need to know some bit of information about every subset of the edge set, of the element set. In some sense, you need to know 2 to the e bits of information. I mean, some of them are determined by the others, but some, you can't substantially reduce it, except in special cases. But for this size, it doesn't really matter. Even if we listed all of the rank of every subset, that would be a list of 512 numbers, and that's small, right? So we didn't, of course. What we actually used was the list of hyperplanes. That's flats of the maximal rank, -1. And internally, for programming, we use the lattice of flats, which I'll explain in a second. And for isomorphism checking, we use the point hyperplane graph. So we made a graph with points, with vertices being the points of the matroid and the hyperplanes of the matroid. Vertices, a hyperplane is adjacent to the points it contains, and then isomorphism on that bipartite graph is just isomorphism in matroids.
Which you were telling just yesterday.
That's right.
It's just the hardest case.
For projective planes, it's the hardest case, yeah. But these are very far from being projective planes. So projective planes are very special matroids that have a super lot of structure, yeah. But in general, these are sort of just smallish graphs, and that's very easy to do.
Can you say a bit more about what you mean by internally and externally?
Oh, sorry. Externally to our program. So we to move data from one program to another, we just store the list of hyperplanes and spit it out. Within the program, we compute the lattice of flats from the list of hyperplanes, manipulate the lattice of flats, and then push out hyperplanes again. So there's a translation involved. Okay, what is the lattice of flats? Well, there's a matroid. The flats are the maximum subsets of each given rank. So these are all the rank 1 flats. These are all the rank 2 flats. And this is rank 3. This tells you the rank of any set, because if we want to know the rank of, say, what's the rank of, 163, say. Well, 16 has got rank 2. If you add an element to it, it's has to go up in rank, so it's got rank 3. What about the rank of 013? Well, that's there, and we already know it's got rank 2. So the flats tell you all that you need to know about or from the flats, the lattice of flats, you can deduce all the ranks. Okay, why do we use that? We use it because of Crapo's theory of extending a matroid, which takes a matroid of a certain size and builds it up by adding one more element. And the way it's going to do it is it's going to take this lattice of flats and it's going to generate the lattice of flats of a matroid with an extra element added. U stands for upper, L stands for lower. So U is the matroid we're constructing, L is the matroid we're starting from. We're going to add the element E. We know from general theory that the flats of U are either flats of L that are unchanged, they're just flats in the new matroid as well, or they're flats of L with the extra element added, or possibly both. Possibly a flat of L might stay a flat and the element E added is also a new flat. So that tells us that for the flats in the lower object, there are 3 possibilities. Either it becomes a flat of the upper object, and when you add E, it becomes a flat of the upper object. So it generates 2 flats in the new lattice. Or it generates 1 flat in the new lattice, and it's either F with E added, or it's F without E added. The other way around. It's either F, so it's either F without E added, or it's F with E added. So there are 3 possibilities.
But there are further compatibilities between different flats, or these 3 to the k are all good?
No, that's the point. So if I give you a partition into 3 parts, then that will give you a recipe for generating the upper lattice, right? You just add, keep this, add E to this, and so on. It would be impossible to do if every partition into 3 bits was feasible, but Crapo demonstrated how to compute the feasible or the properties of a feasible partition, and these are things that are called modular cuts. Here's a proof by example. Definition by example. The properties of a modular cut are as follows. It must be an upset in the lattice. So if something's in the modular cut, then everything above it must be in the modular cut. It must be closed under meet in the lattice. So it must be an upset closed under meet. Apart from that, there's no conditions. This is closed under meet because the meet of this and this is this itself. And there's nothing else to check. It's an upset because this and there. Okay. Once you've chosen a modular cut, then everything that is covered by an element in the modular cut, the green things, in other words, with just one line going down, is called the collar, and everything else is called the rest. And the key point is that this partition, F1, F2, and F3, is exactly this partition, 1, 2, and 3. So, all you have to do is find the modular cuts, and then this is given and this is given. So instead of being a partition into 3 parts, it's essentially just a special subset called a modular cut. Once you've found that special subset, then you just build the bigger matroid by doing the following the rules. And that gives you a new lattice of flats and blah, blah, blah. Okay. We decided that it would be important to use an orderly algorithm to do this process. So an orderly algorithm is a combinatorial algorithm with a property that no two of its outputs are isomorphic. Okay, now that's a very important property for a generation algorithm to have, because suppose you had to do a post-processing check for isomorphic things. Okay, well then you might list 100 million things, and then you've got to check 1 against 2 to see they're isomorphic, and 1 against 3, and 1 against 4, and you've got to keep your 100 million things. You never know whether something you found here is going to be isomorphic to something way later. So somehow you've got to do all these comparisons.
It's like in theory, you want some invariant.
That's right, but you need a complete invariant. It needs to be perfect.
Well, if you have a subcomplete invariant, you will have to test isomorphism on small bunches, and that's fast.
That's right. In some sense, you need to have something that guarantees that chunks are different. Yeah. Why are these algorithms basically important? Well, you can partition the search between multiple computers. You can generate vast catalogs because you just keep going and writing them to, examining them or writing them to disk or something. Or you need not even store them, you can just count them.
And usually you could partition the algorithm off different computers because you kind of know what order these things are going to come out in.
Well, it's sort of structured in a tree-like way, and you can go to sort of depth 3 or something, and then you have a whole set of nodes and put one node on each computer.
Right.
Yeah.
In the tree partition of before,
Yep.
if you want to write down the base going down and the base going up, that one are also exponentially large typically?
Yeah, they could be. There's no... Yep. This is strictly, it's only going to work for small element numbers. There are 11 billion Steiner triple systems of order 19. That's sort of an orderly algorithm, like example case. Computed just by compute and throw away, just counting them. So I didn't store anything about them. So.
How long did that take?
I don't know. It was done a couple of years ago. I think it took a couple of months. A couple of years ago on a number of computers. So, okay, so here's the algorithm. L of k...
What if there is a mistake in the program? How do you know that...
That's right. It's rather unsatisfactory to count and throw away because, someone could come along and say, well, I think it's a 3-0 there.
Oh, so you don't actually keep a list of...
No, that's right, because they're too big. You can't store 11 billion of them. This isn't mine. This is somebody else's, I hasten to add.
You can't store 11 million?
Well, Steiner triple system's got 57 blocks, and if you've got 11 billion things that have got 57 integers.
It's not 11 millions, it's 11 billions.
But each one doesn't I mean, how many bytes does it take to store?
Probably, I don't know, 57 times 3 times 4.
Anyway.
Well, the way disk space is going, it's not so bad.
Yeah, it's the difference for 2 years ago.
That's right.
500 gigabytes, you buy not with the grant.
That's right. Yeah, exactly. You just. Okay, so here's the orderly algorithm for matroids. L of k is going to be our list containing one representative from each k element matroid. So we're going to start with L2 or something like that. And we're going to process each matroid in turn. For each matroid L, we're going to form a set X of L, which stands for the extensions of L, in the following fashion. Compute all the single element extensions L primed by finding modular cuts and adding the element in the special way. Canonically label the point hyperplane graph. So that means form the point hyperplane graph, use the canonical labeling algorithm of Naughty, Brendan McKay's program Naughty. So the canonical labeling algorithm takes in a graph and spits out a distinguished copy of that graph in such a way that if you put any isomorph into the algorithm, you always get the same one back out again. So it allows you to identify vertices in the graph in a labeling independent fashion. It doesn't matter how it came in labeled. Once you've done this process, you've got it in the standard labeling and you can work with it.
How many, that works well for how large graphs?
Oh, well, we were talking yesterday. In practice, apart from projective planes and some other highly structured graphs, graph isomorphism is easy. So 10,000 vertices, 20, 50,000 vertices, yeah. But even a projective plane on 500 vertices is can cause trouble.
It would have been really nice if during that processing you could have written down how many steps did the algorithm take for every sample and make the distribution in order to understand how do the bad ones arise.
Yeah.
The histogram.
Yes, no, that's true. Yeah. But the trouble is there are so many graphs. It's hard to find hard examples for Brendan's program. Anyway, we canonically label the point hyperplane graph of L primed, which is this newly created extension. And then we look at the new point that we've just added. We say, is that in the lowest canonically labeled point? Or is it in the same orbit as the lowest canonically labeled point?
Orbit means under the isomorphism?
Under the automorphism group of the matroid, yeah. If it is, then we accept the output, adding it to X of L. If it's not, we just throw the output away and we ignore it.
And the reason is because it will be found as a single element, the same thing will be found as a single element extension of some other K element.
Exactly. So the whole point is, what we're doing in this fashion is we're distinguishing a way of building that new matroid, and we're only accepting it if it comes from that distinguished way. If it's constructed somewhere else later, we have to identify, well, it didn't come in the proper way, so we'll throw it away.
And you can the point is you can throw it away without having to compare it to
Exactly. You just have to say, did it get built the right way? If it didn't, throw it away. We didn't, and then we did actually just, I mean, you could do more, but we then just removed all the isomorphs from X of L by pairwise comparisons. You still might get isomorphs, but this step guarantees that X of L1 and X of L2 are guaranteed to be different, but X of L itself may still contain isomorphs because there might be isomorphic modular cuts that we've built up.
But typically for an 8-element matroid, and you want to go up to 9, how many modular cuts would there be for a given one?
Oh, maybe it varies a lot, but for the worst ones, maybe a few 100,000.
A few 100,000 single element extensions in one matroid.
That's right. Only a few of them get accepted, and then we.
Oh, I see. So these pairwise comparisons are over a fairly small set.
That's right. Okay, let's.
How do you find the
So
maximum cone?
instead of just removing, you were writing down, you were not writing down the size of the automorphic group, but only of the orbit of the stabilizer, what it is.
Well, when Naughty does its work, it will tell you what the orbits are of the points, so you'll know which points are in which orbit.
So for a database, you would like to really write down because.
Oh, ultimately, ultimately you
want
keep
to
it,
write
but just
down.
in the construction phase, we'll do all the database stuff later. I mean, at the end of the construction.
Are you going to tell us how you find the modular cone?
Oh, yes, I can if you'd like.
No, I was wondering if it was going to come there.
No, it's not. I was assuming that was sort of given. All we do actually is we sort of cheat again. Basically, the way I work is that you write the simple but working program, and then if it needs to be refined, you then refine it to a better one, but at least you've got the working one. In this case, it turned out that the first one worked well enough, so we'd never. What you do is you can observe from this example that the bottom elements of your modular cut must be an anti-chain in the matroid, in the lattice. Well, there it is. It's just one element, clearly an anti-chain. But in general, it must be an anti-chain. So all we did was search for anti-chains within the lattice in every possible way, form their upsets, and confirm that it was closed under meet. Okay? We may need to do something more clever for a subsequent project.
I will not ask what is an antichain.
A set of mutually incomparable elements. So a modular, the bottom of a modular cut can't contain both this and this, for example, because
Oh, sorry, which are this and this?
2 and 0.2. Taking the least elements in the modular cut.
Right.
So that's going to be an anti-chain in the lattice, set of mutually incomparable objects. We just search for them using a sort of independent set in a graph routine sort of thing, and then form the upset. That's your candidate modular cut, and then
Didn't the modular cut have to be closed under meet?
and then check that it's closed under meet. And and you get, there are a lot of anti-chains that don't give you modular cuts.
Oh, okay.
Yeah,
But the point is, even the number of anti-chains is reasonable.
that's right. In practice, we discovered that about half of the anti-chains gave modular cuts. So
And you can generate the anti-chains in time roughly proportional to the number of them.
yeah, roughly.
And the reason is that the rank is always low up to these low sizes. If the rank was high, it would be rare that they are good.
If the rank is high and you've got no collapse early, so that the lower levels of the lattice are just all the 1 sets, all the 2 sets, all the 3 sets, all the 4 sets, then you start to get problems. Okay, so then the theorem is, or the sort of standard orderly algorithm theorem is that the set of all objects on k+1 things is just the union of all of these extensions that you've done.
And that's disjoint union.
That's a disjoint union. Yeah, disjoint union.
That's the key thing.
That's right, yeah. And it's easy. The matroids in X of L are pairwise non-isomorphic, well, because we did that last processing step to throw away isomorphs. So within each individual blob, they're non-isomorphic. If L1 and L2 are not isomorphic, then the extension X of L1 and X of L2 do not contain isomorphic matroids. Can't contain isomorphic matroids, because if U is a k+1 element matroid and E is its lowest canonically labeled element, then you only accept it when it comes from U delete E. If it comes from U delete something else that's not equivalent to E, then you reject it. So that partitions a search into, so you can start with your 1724 k-element matroids, 8-element matroids, and run the algorithm on each of those, and that will give you 1724 mini computations that you then, and that gives you all the 9-element matroids. And that's the answer. They were off by a bit. So the number increases, but less than we had thought, and in fact this whole computation took a few hours on a modern machine. So started off one night and came back in the next day and it was done, sort of thing. What can we say? Well, rank 4, 190, size 9, rank 4, 190,000 Matroids, you know. So it's growing, nice and, you know, it's growing fairly fast, but it's not horrific.
And it's already submitted to Zoan, Encyclopedia, and things like that.
That's right, yeah. Yep. Yeah.
Do you have any idea, oh, I guess you're probably going to say, do you have any idea what the rate of growth of this thing is?
No one has any firm idea. There's sort of some doubly exponential lower bounds known.
I see, so looking at it, you can't guess.
No, that doesn't.
You don't have enough terms.
That's right.
Are most of them non-representative?
At this stage, okay, 1724, there are 44 that are not representable.
Oh, I'm sorry.
So most of them are representative.
So
On 8.
on 8 elements, 44 out of 1724 are not representable.
For 1724, for all of those, the calculation has been done.
Correct.
About their complete representability, or
Whether they are representable or not.
not which fields?
Not which fields, no.
I see. But is there an algorithm for checking, or do you have to like invent a proof for each one of the 1724?
That's a question that I can't work out the answer to.
Or I mean, some of them probably are easily seen to be representable over some field or other,
That's right.
but which you can do algorithmically. But then after you've checked 100 fields, you stop and you guess that it might be non-representable, and then you ad hoc come up with a proof.
That's right.
On my word.
There is any natural set of fields you would like, maybe GF2, GF3, 6 root, and then the rest of the world, or this is not a sensitive question?
It is sensible, yeah. I mean, the short answer is there's no pump a Matroid in and turn the handle and get out whether it's representable or not. For any specific field you can do it, except that the complexity, I mean the time consumed grows dramatically, and you also run into some other problems, technical problems.
Also for infinite, like
Luckily we don't have to worry, because if a Matroid is representable over an infinite field, then it's representable over some finite field. So we can forget about infinite fields. Unless you're interested in specifically which are real representable, but I don't even have an idea how to start that on a computer. So, okay, let's.
And for this 9 elements, does it change the ratio representation?
At 9 elements, there are about 50,000 that are not representable. About
a much bigger fraction.
That's right. About 50,000 that are not representable, 327,000 that are definitely representable, and 6,000 that I don't know and can't work out.
And the you didn't construct 50,000 separate proofs.
No. But your 44 8-element Matroids each have extensions, and they can't be representable either.
That's 50,000.
And that comes to 50,000 roughly. Yeah.
So 50,000 corollaries.
That's right.
So there's no good, decent, even sufficient condition for a Matroid being non-representable, other than the fact that it has a minor that you already know.
That's right. There is a condition by Ingleton which boils down when you, I mean, computationally, it appears to boil down to, has the Varmosh Matroid as a minor? But it's, I mean, I don't think he knew that when he gave that condition.
But now you know that instead of one guy on 8 elements, there are actually 55.
That's right,
or whatever
yeah.
it was.
Yeah.
So let me ask you a question that was maybe that's already known. If I remember it correctly, there was a question whether any transversal matrix is represented. Is it, or do I remember it wrong?
I don't know that. I don't know what the, I mean, there are lots of questions that I don't know.
If I'm remembering Oxford's book correctly, I thought a transversal matroid was representable over every sufficiently large field.
Transversal matroids should be representable because you can sort of form them by taking a frame and putting points on the lines or the flats, the facets of that sort of polytope, and then throwing away the points.
So they are representable?
They should be over some big enough field, yeah.
So
I think, anyway. Okay. I've almost finished part 2 of my 3-part talk. But I won't give you the 3rd part, I'll stop at part 2. Let me just talk about paving matroids. Because paving matroids are the bane of our life. Because a paving matroid is a matroid that has no small circuits. In other words, the circuits are essentially as big as they can be. I mean, uniform matroids have circuits. The smallest circuit in a uniform matroid is r plus 1. Well, when you've got r plus 1 elements, you have to be a circuit because you can't be independent anymore. A paving matroid is a matroid that has everything independent, and the first circuit is size r.
What's the difference between having no circuits of size less than r and having geared r?
And they're synonyms. You can use the same phrase if you want
Just
to.
geared is for graphs and this for general.
Some people use the phrase girth for matroids as well, and you're free to use it.
This would be analogous to saying the length of the shortest cycle is the same as the number of edges in a spanning tree, which can't happen for graphs.
Oh, yeah, no, you can't have a paving matroid that it's a graph, but what he was saying is you can just call this definition could just be expressed as the girth of the matroid is at least r. Okay, now paving matroids have a very special structure because the hyperplanes form a design theory type object called an r-1 partition, which I'm going to define again by example. This set of subsets of a set is a 2 partition because every 2-element subset of 0, 1 through 6 occurs in exactly one of them. This is also a 2 partition. You see, I've just put in 0, 1, 2, 3 and 4, 5, 6, and then any 2 set that I've left out is going to be, I'm going to add to it. Okay?
Is this a cycle?
So that's a 2 partition.
This concept exists out of Matroid theory.
Oh yeah, of course, yeah. If you were a design theorist, you would call this a pairwise balanced design. It's a block design with the blocks of different sizes, if you like. And this is natural, this is the Fano plane, just expressed in a less attractive than usual fashion. Okay, the point is that any r-1 partition gives you a paving matroid. Now, there are some special paving matroids where all the hyperplanes have size only r-1 and r. And they're called sparse paving matroids. And I can just tell you the ones that have size r, because the ones with size r will cover a whole bunch of r-1 sets, and there'll be some r-1 sets left over, but we just take all of those to fill out our sparse paving matroid. So, a sparse paving matroid of size 10 and rank 5 is determined by a collection of 5 subsets that do not intersect in a set of size 4. You just take a bunch of 5 subsets, and then you just take any 4 subsets that are left that are not covered. Okay, that's a graph. We know its maximum independent set size, and every independent set in that graph gives you a sparse paving matroid. How many are there? Well, we don't know. But sampling, computationally, we estimate that there are about 2.65 times 10 to the 12.
What does it mean sampling? You can sample uniformly or?
I ran the orderly algorithm to size 10, got 20 million starting points, and then took 0.02% of those and ran them to completion, and then multiplied the number by.
So you have kind of excess sampling at the intermediate part of the tree, and
That's
you
right.
hope that the branches, if you have many of them, they are almost similar.
That's right. I mean, it could be hopelessly wrong. In practice, when we've done this before, it seems to be okay, roughly. But it's not rigorous at all. But anyway, the point is there's a lot.
Well, if the second moment of the distribution of your branches is really small, you start believing.
Yeah. It was never clear to me whether you could actually do any rigorous statistics on that sort of thing. I mean, in principle, there's nothing to stop an orderly algorithm having 0, 0, 0, 0, 2 trillion from one branch and then zeros from all the rest. And if you sample it, then, you know. So I tried to look up some stuff about statistics of of these things, and the best I could come up with was someone who said that naturally occurring distributions can be sampled and use the central limit theorem and stuff like that. But this is not a naturally occurring distribution. This is a highly Anyway, I don't know anything about this sort of sampling. But if anyone does, and I know there are people here who probably do, then a better estimate on that. Anyway, that tells you why we didn't bother to do 10-element matroids, because even with paving matroids and even with sparse paving matroids, we're already looking at around 3 trillion of them. Now, even at 1 byte, even at 1 bit to store each one, which is clearly ambitious, we still couldn't store that on any modern equipment.
In a few years you can.
Yeah, in a few years. But then the 1 bit per, we might have to extend. We might need more than 1 bit per.
Well, you could probably pack a few thousand matroids into a single bit by then.
And I will stop there. I won't tell you about the database and searching it and all the rest of it. I'll just stop with that computation. I can always do a part 2 later in the semester if anyone's interested.
So the point is you have this database and then you can use it for various things.
That's right.
I mean, conjectures
That's right.
that had been made, you may be able to find 9-element counterexamples where there were
Exactly.
10-element counterexamples.
Yeah. Yeah, you got it. So I'll just quickly
And
show
you'll
you.
make this database available in some form that's
That's
actually...
right. So this is sort of the question that I get from people, apart from my many offers to get a new job to work from home and to buy a sparkling fake Rolex that will impress my friends.
Fake Viagra.
Fake Viagra. Yeah. So Stefan van Zwaan wanted to know a 3-connected, non-binary, non-ternary, GF4 representable, uniquely GF5 representable Matroid, and
This was one of the good questions.
yeah, that's right.
So
So
you haven't yet gone through your catalog and computed all of these things?
yes, I have, luckily. So I've done most of the computations for those things. So I could actually just
You spit out the answer.
do it. So it's actually in a MySQL database, and you select the ID from Matroids, join Matroid 9 reps where is binary is 0, is ternary is 0, num GF4 reps is bigger than 0, and so on.
Oh, wow.
and then that pops
What's
out.
the answer? You have 230?
233 of them. So yes.
And you sent him those 230?
That's right. Yeah. So
I mean,
he.
you wanted one example.
Well, I told him that there were 233 and sent him one. Yeah.
You have to make a Java program on a website.
Well, it is on a website. So there you can sort of browse the Matroid. So that's Matroid number 298, and you can see that it's got size 7 and rank 3, and it's Stefano plane, and it's got 16 flats and group size 168 and minimum circuit size 3, and so on. So you can do that. A lot more needs to be done before this is really used.
But the representabilities are listed there too?
Some of them are. Binary, ternary, quaternary is. The other ones are stored in a different table of the database and not currently hooked in, but I've got them, information. Yep. I've got the complete information for representability up to GF16. So, okay, thank you. I think I'll stop because I'm already over. So, as I said, just a little story to tell you that doesn't involve too much expenditure of mental energy. And you all asked the questions during the talk, so let's just go and have a cup of coffee.
If you were to do, sorry.
That's all right.
If you were to do the 10-element stuff,
Yeah.
right? I mean, it does. I mean, disks are growing so fast. I mean, two terabytes, I think, is what we have on our cluster at NYU for $100,000. So a real, I mean, Tony Goodman must have easily 10 or 100 terabytes on his computer. So the storage is probably not such a big deal. But what would the CPU time be to do that?
CPU time to do the 2 trillion sparse paving matroids just as independent sets, I estimated it was 200 CPU units.
Okay, well,
That's doable.
that's. I mean, Tony Goodman has a